Hi, welcome to this video about shale gas and fracking. You've probably heard a lot about these topics, so why are they important? Well, one thing is that the U.S. has a huge supply of gas, mostly in the form of shale gas, and the low cost means that shale gas is going to play a really important role in our energy future for years to come. So given that, it's really critical to understand what the environmental risks might be of extracting gas, especially by fracking. So just to hit that point home, here's the latest energy forecast for the United States. This is total energy consumption, and you can see natural gas is rising faster than any other energy source in our country. It's risen hugely over the last 10 years, and it's projected to keep rising. And the main reason for that rise is shale gas. So we're going to talk about how shale gas differs from conventional gas in this video. But for now, the motivation is this plot here. Look at how the production of shale gas has increased over the last 10 years and how it's forecast to increase. Everything else is going down, shale gas is going up. And that's largely because of new discoveries in the eastern U.S., although also down in the southeastern U.S. as well. But you can see that the Northeast is now really getting into the energy game because it turns out there's a lot of shale gas stored there, and that's been being exploited cheaply and quickly. All right, so in this video, we'll look at the basics of shale gas. What is it? How does it form? Then we'll look at an example, the Marcellus Shale, and then we'll finish by talking about some of the basics of fracking and some of the things that control the risks associated with fracking. So just a quick reminder, what is natural gas? These are hydrocarbons, just like oil, just like rubber. It's a bunch of hydrogen molecules bonded to carbon. The gases are unique because they have the highest density of hydrogen bonds per carbon, which means they release the most energy for the least CO2. So they're nice little nuggets of high density energy. And because they're in a gas form, their extraction is typically very pure. There's very little refining associated with gas. You pretty much pull it out of the ground, put it right into the pipeline. So you don't have a lot of those collateral energy expenditures. Also, because it's a gas, it leaves all the toxic stuff behind. The sulfur, the nitrogen, the metals, all these things that you might find in coal or even petroleum are not in gas at all. So it's very clean. So it's got a lot going for it. Of course, it's still a hydrocarbon. Of course, gas is produced by burying organic material and heating it to about 120 degrees Celsius. And traditionally, that gas forms at some depth, maybe a few to 10 kilometers below the surface, and that gas would then migrate up into a trap where it would be cohabitating with oil. And you might just drill it out of a conventional oil trap. And we've talked about that in other videos. But in this video, we're really going to focus on this idea of shale gas. It's a little bit unconventional, and it's very different than traditional gas. And here's the reason. Instead of being trapped in some kind of very porous, permeable sandstone, shale gas is trapped in tiny pore spaces in shale rock, okay? So here's what that might look like: an outcrop, a bunch of black, organic rich shale. Here's what might look like a drill core through the shale. And then here's the microscopic level. Look at these little pores right here. They're only less than a micron in diameter. But if you get enough of these pores, they can actually hold a lot of trapped gas. Now the key thing is that they are not connected, okay? This shale has a high porosity, it has a lot of holes, but it has a low permeability, meaning those holes are not connected and the gas cannot permeate or move through the rock. So high porosity, but a low permeability. Basically, the gas is trapped in these little pores in the shale. Now, how do we get it out? You already know the answer. We need to crack the rock. We need to frack it. And by fracking, these cracks are going to actually come through the rock, and they're going to connect up these pore spaces and let the gas flow out of the pore spaces and up through a wellhead where we can capture it. Okay, so that's really the basics of shale gas. So why has this been a revolution in the last 10 years? Well, basically, it's been the realization that rocks we already knew existed, like the Marcellus Shale, actually were full of gas. And coupled with some technological advancements in fracking that have allowed us to actually get at that gas. So here's a little map of really important shale gas plays in the U.S. Here's the Marcellus up here. It's outlined in blue. And there's also a couple other formations, the Utica and the Ohio formations. So these are all kind of associated. All of them are gas bearing. And you'll note that really Pennsylvania has been kind of the heart of this fracking boom in the Northeast. A lot of these formations are really centered over Pennsylvania. So that's where a lot of the action has been. Again, here's what that looks like in outcrop. It's a shale rock. You can see it's a fine-grained, dark-colored. It's pretty much falling apart and kind of crumbling in the outcrop, which is pretty typical of shale. And a few words about where this was deposited and a little bit about the geologic history of the Marcellus Shale. It was deposited about 385 million years ago, okay? And that was a time when the tectonic configuration of the northeastern U.S. was very different. We had recently built a couple mountain building events, the Taconic orogeny, followed by the Acadian orogeny, and we basically had a pretty good-sized mountain belt extending from New England down through Pennsylvania and towards Virginia. You might think of this as the Proto-Appalachians, okay? But also at that time, sea levels were a bit higher. So in addition to the main ocean, we had some inland ocean basins, like this one called the Appalachian Basin, okay? And this was ripe for deposition of sedimentary rocks. There was lots of sediment coming off of this Proto-Appalachians. It was probably warm and nutrient rich, so there was a lot of algal activity, a lot of plankton growing, and other organic life in this basin. As that organic material settled out, that was the source rock for the gas. Those were the organic rich shales. And ultimately, those are going to be buried by sands of the Catskill Delta. As rivers here deliver sediment westward, and we're able to actually build out a sand-rich delta structure that's going to come out, advance over those organic shales, and bury them, and heat them, and make gas. So here's what this looks like today. All right, Ohio is out here, Pennsylvania is over here, and the Proto-Appalachians would have been just off the screen to our right. So these are the sediments that were laid down in that Appalachian Basin. And as I just said, we have a lot of shale rocks that were deposited in the deeper water, like the Marcellus. These are organic rich shales. And as you move up, they're covered by clastic sands of the overlying delta sediments as that Catskill Delta advanced out over the basin. Also notice that the Marcellus Shale is in places quite deep. In parts of Pennsylvania, it's about 8,000 feet deep. So that puts it at about 1.5 miles depth at its deepest. That means that it's very thermally mature, it's been heated, and we're also going to find out that that may mean it's a little bit safer to frack if it's way down at that depth. And so just to finish this example of the Marcellus Shale, here's a map of recently drilled gas wells, which we would call unconventional wells because they've probably been drilled into shale and fracked to get gas. And this really just illustrates the explosion in gas exploration in Pennsylvania. You can't even see any black or gray dots, barely. These are wells that were drilled about 10 years ago. And as we come into the greens and the blues and the red, these are all wells that were drilled basically in the last 5 years. So you can see in the last 5 years, we went from having very few wells to having a lot of wells, a huge fracking boom in Pennsylvania. Okay, so now let's look at how fracking works. How does it work and why is it potentially risky? Well, the basic idea is this. We've got our layers of sedimentary rock, and down here at about 8,000 feet, we've got the Marcellus Shale, okay? So we set up a well pad on the surface, and we drill. Often we're able to drill a curved hole so that it turns flat and actually follows along a certain sedimentary layer for a long distance. Once the drill hole is situated correctly, a lot of fluid is brought in, and that fluid is pumped into the well at very high pressure. And pressures that are high enough to actually induce fractures in the rock. And that fracking fluid includes other things like proppants. Proppants are sand that helps to keep the cracks open. If you don't have that sand or other granular material in there, then you're going to make the crack and it's just going to close right back up again under pressure. So the idea is to keep those cracks open so that the gas can then flow out of the crack and back up the well to the surface. And so that's the idea of fracking. It can take place at any depth. In this example, it's taking place at about 8,000 feet. In other places, other examples, it may be taking place much shallower, sometimes within a few thousand feet of the surface. And we're going to talk about why it gets more dangerous as you get closer to the surface. The other thing I'll just point out here is this well casing right here. Typically, these wells are going to pass through the water table. And usually groundwater that's used for drinking is often sourced from within 1,000 feet of the surface, okay, so, or a couple thousand feet of the surface. So it's this upper part of the well that gets extra thick casing that would usually be concrete of some kind. And the goal there is to make sure that fracking fluids don't escape from the well into the surrounding rock, or that gas coming out the hole doesn't escape from the well into the surrounding rocks. So we're going to see that it's very important to have quality casing here in the upper part of your well, because that is where your well is in direct contact with shallow drinking water aquifers. And if we contaminate those aquifers, that's a huge mistake and a huge risk of fracking. Okay, so those are some of the basics of fracking. Obviously, there's a big debate about this. There's some huge benefits. It's a domestic source of clean natural gas, and it can bring revenues to rural areas. It can create a lot of jobs in the industrial sector and be a huge economic driver. So fracking brings a lot of benefits. It also brings a lot of risks. And we'll break those out here. The three main risks are contamination of shallow aquifers by gases, okay? And then the second one is contamination of shallow aquifers by drilling fluids. And these are a bit different from each other, although they both would potentially contaminate a shallow aquifer. A third risk is the release of gases like methane that drive global warming. Methane is roughly a 600 times more effective greenhouse gas than CO2. So if we even leak a little bit of methane via fracking, if we don't capture it all and burn it, but if it leaks into the atmosphere, we could actually potentially be having a huge impact on global warming. And that's something that's currently under study. All right, so let's look at these risks one by one here. So what controls the risk of aquifer contamination by gases? A huge factor is the depth of the fracking, okay? We talked about how the aquifer, the shallow aquifers, are usually within a couple thousand feet of the surface. So if you're fracking at 8,000 feet, you're probably pretty well buffered from that aquifer. However, if you're fracking at 2,000 feet, you're going to be a lot closer. So right away, the depth of fracking is probably the number one factor that determines the risk of the fracking. The closer you are to that groundwater aquifer, the more risk there is. Now, another huge factor is what kind of rock layers are between your fracked layer and the shallow aquifer, okay? Ideally, we want impermeable rock layers, basically things like more shale between the fracking and the groundwater. If you have a lot of permeable rocks in here, gas is going to be able to just rise straight up and get right into your shallow aquifer. Another factor is the presence of vertical fractures. If you have rock that is heavily fractured with little faults or fractures, gas can make its way through those fractures up into the shallow aquifers. So really the permeability of this intervening rock is hugely important. And then the third thing is the quality of the well casing at shallow depths. So we just talked about how this upper part of the well is cased very carefully, we hope. And if it's not cased carefully, leaks can develop. Pressures are very high in the drill hole, so fluids can escape, gases can escape right into that shallow aquifer. So this well casing is a really important factor in thinking about risk of contamination by gas. And just an example of this, here's a woman in Pennsylvania setting fire to her tap water, which obviously has been accumulating methane to the point that it actually was flammable coming out of her tap. So it's a real thing. It's not incredibly common, but this does happen, that gases head upwards into groundwater. Okay, so the second point, what controls the risk of aquifer contamination by fracking fluids? And this is similar to gases, but it's a little bit different. Fluids behave a little bit different than gases in the deep subsurface, okay? And the main difference is that groundwater generally flows downward or flows laterally. It can flow up, but it's not that common. Whereas gas just inherently bubbles upwards because it's less dense. So the key difference between gas and fluids is that groundwater generally doesn't flow upwards, which makes it less risky. Nonetheless, the risk factors are pretty similar. How deep are you fracking? Okay, deeper is always safer. And then what's the quality of the well casing? The same concept we just talked about. And then one other one that's unique to fracking fluids is really how are these fluids handled and stored on the surface? As I said, it takes a huge amount of fluid to do the fracking. And when that comes back out, it's got all kinds of stuff in it, and it also may have a lot of briny groundwater, deep groundwater that actually isn't suitable for release into the shallow subsurface. So basically we got a bunch of nasty water, and we have to make sure that doesn't get spilled or leaked into shallow aquifers. And just an example of that, here's a typical fracking pad, okay? Here's the drill. Here's a little repository of drilling mud, basically. And I believe this is a pond meant to store fluids, fracking fluids, and any kind of fluids that come out of the hole along with the gas. So You can see that this pond is man-made. It's lined with a heavy-duty liner, and the hope is that this fluid is not going to leak out of this pond into the subsurface aquifer. If it does, we've got some contamination issues for sure. And just for scale, here's the neighbor's swimming pool here. So, that's a lot of water potentially contaminated. All right, so let's just finish with this idea of what happens if we do contaminate shallow groundwater with fracking fluid. What's actually in it? How bad is it? And the answer is it's not terrible, but it's certainly not something you want to be drinking. It does have a number of organic constituents, like are listed in this woman's sign. And here's some of the main ingredients of fracking fluid. It's mostly water, mostly sand, with trace amounts of these chemicals. Some of these are, well, most of these are kind of household chemicals. Nonetheless, they're things you really don't want to be drinking, of course. And finally, what's the environmental record of fracking? The environmental record is actually pretty good. There's only a few proven cases where fracking chemicals have ended up in groundwater, and some of these are hotly debated. That said, it's extremely difficult to prove that either fluids or gases came from fracking. And one reason for this is that things like gas are usually already present in an area where you would be fracking, because that's why you're fracking, is because there's already gas there. So it can be hard to tell whether that gas was naturally released or whether it was released by fracking. And usually there's no baseline data set. There's no quote-unquote before data set that you could compare with. So it can be very hard to tell if gas contamination came from fracking or not. Fluids are a little easier because there may be chemical signatures in the fracking fluid. And one famous case is the Pavilion gas field in Wyoming. This was very shallow fracking, I think about 1,000 feet depth or a little more. And it seems likely that there was contamination here, although it has been hotly debated, and we'll actually take up that debate in class. So thanks for listening. Here's a summary of the key points of this video. And here's a concept questions. Hopefully you could answer these after watching this video. Thanks very much.